Hello, welcome to Soft Purpose channel. I'm Godfrey. In this video, I'm solving a Cambridge Air 2 Physics question on direct sensing. This was a 2019 November exam series. It's always a good idea to do your revision topic-wise. When you read a given topic and attempt questions when the content is fresh in your mind, you get the most out of this of the topic. You do all the topic questions topic-wise, questions on 2019, 2018, going backwards. This way, you'll be sure that you're well prepared. Come exam, you'll be confident and you'll get your A star. I'm sure that is what you love most in physics, A level. If you have not yet already subscribed to my channel, please click the subscribe button and hit the bell icon below. This way, you will be notified every time I upload a new video. We are getting started. This question on direct sensing was set on paper 4.1, October, November, and this was question number 7. So you can use this in every question that I am going to solve. You'll be getting this. 9702, that's the code for A-level physics in CIE. So you can refer, you can just get this code here, writing here, to be able to refer to the past paper for variant 4.1. And of course, if you want to check on the marking scheme, you can as well know which question and where to locate it. Very well, let's get started. An ideal operational amplifier pump has infinite bandwidth and zero output impedance. What is meant by infinite bandwidth? Of course, infinite bandwidth basically means that the amplification is the same for all frequencies. So all frequencies are amplified by the same factor. So infinite bandwidth basically means that all frequencies that will input in the op amp are going to be amplified by the same factor, amplified by the same factor. If the amplification is by 10, then all of them will be amplified by 10. State what is meant by zero output impedance. This means that zero output impedance means that the whole of the output voltage is provided across the output load, and there is no resistance at all to the output signal that is going to come out of the op amp. So say the whole of the output voltage is provided across the output load. That load could be a lamp. That load could be anything that you want to output your voltage. Part B, the circuit for a non-inverting amplifier incorporating an ideal op amp is shown in Fig 7.1. Fig 7.1 is this one. You can see the op amp is that. It's powered by a voltage of 5 ohms, 5 volts. Of course, it has got a resistance there of 4 kilo ohms. Light emitting diode resistance, the resistance of 800 volts, 800 ohms, V out and V in. The light emitting diode emits light when the potential difference across it is at least 2 volts, at least 2 volts. Below 2 volts, it will not emit light. Okay. The current in the LED must not be greater than 220 milliamperes or milliamps. So that is a condition. So calculate the gain of the amplifier circuit. Calculate the gain of the amplifier circuit. Of course, we know that gain, which is G, is equals to V out over voltage in. And of course, for non-inverting amplifier, the equation is usually 1 plus resistance RF over R in. Of course, in this case, our RF return frequency is this one, 4000 ohms, and our R in is this one. You can see this one is R in there, and this is the resistance of the return signal. So this equation is 1 plus 4000 ohms, of course, over 800 ohms. Of course, the ohms will cancel, and of course, when you do a good calculation, 800 divided by 400 divided by 800, that will cancel. So this basically will be 5. So this will be 1 plus 5, which is equals to 6. So the gain will be 6. Oh, very well. Part 2 of B, determine the value of V in, for which the value of V out is plus 2 volts. Of course, since you have gotten the gain is equals to V out over V in. We want the value of V in when the V out is this. So V in is equals to V out over gain, in which case our V out here is plus 2 volts over 6, which is the gain, which I've calculated up there. So when you calculate this one, you'll get plus 0.33 volts. So V in will be 0.33 plus. Don't forget the plus. It can either be plus or minus the voltage. State the maximum value of the output potential V out. Of course, this is guided by the supply voltage. The maximum V out cannot be greater than the supply voltage, and the supply voltage here, as I said earlier on, is 5 volts. Okay, plus or minus 5 volts. So the supply voltage is 5 volt, 5 plus or minus 5 volts. So we're talking about the maximum. So the maximum here is plus 5.0 volts, right? Minimum will be minus. So the maximum potential will be 5 volts. Okay, could be plus. When the op-amp, part 4, when the op-amp is saturated, the potential difference across the LED is 2.2 volts when it is saturated. When it is producing this voltage as the V out, then that will be the voltage across the LED. Calculate the minimum resistance R so that the current in the LED is limited to 20 milliamps. We want the value for R, the minimum value for R, so that the current flowing through the LED is 20 milliamps. So that's what we need to calculate. Of course, we need to know what is, if the op-amp is, if the LED is the voltage across the LED is 2.2, and we are told the op amp is saturated, because we need to know the voltage across the resistor. Therefore, to get to know that, we take the saturated voltage of the op amp minus the voltage of the LED. This will give us the voltage across the resistance will be 2.8 volts. See the voltage across the resistance. And we know that resistance is equals to volts over current. We are given the current here, and you have calculated the resistance here. So we need now to calculate the minimum resistance of resistor R. So resistor R will be having 2.8 volts across it, and a current of 20 milliamps flow through it. So milli is 10 raised to power 3. Therefore, this will give us a resistance of 140 ohms. So the resistance of resistance R will be 140 ohms. Don't forget, the LED and resistor R are in series. And so the sum of their voltages should be equal to the V out. So V out should be voltage across the resistor R plus voltage across the LED. That's why we have said that to get the voltage of the resistor R, the V out we are given to, because we are told it is saturated, V out is 5 volts minus the voltage across the LED to get VR. So VR was V out minus the voltage across the LED, the LED. Very good. Well, it's great you're watching this video, but remember, practice makes perfect. I encourage you to practice working out these questions yourself as I guide you. You may get this same paper I'm solving right now from this site here, solvedpapers.co.uk. The site I'm talking about is this one right here, if I may show you. This is the site I'm talking about, solvedpapers.co.uk. Take time and look at the site. It's a very resourceful site. You can get this for physics. Of course, there's maths and chemistry, physics 2019 of November. You come here and you'll find we have topical questions on 2019 for November and June. Of course, the other years, as you might have already noticed, 2018, 2017 topicals are right there, 2017. And the paper I'm talking about here, I'm solving right now, is direct sensing. And direct sensing is, you can download this one here. You can also download direct sensing also for June, and also these other topics. I encourage you get all these topical questions. This will help you revise for both November past papers and October, November and June past papers, and of course you'll be set. I've taken time, I've categorized these questions that were set on November and on June topic wise, to make it easier for you to revise topic wise. Read a given topic and come here and get the papers, and then you can revise topic wise. Of course, you can get all this in a zip folder. The zip folder I'm talking about is, you can click here. You can get these papers for 2019, 2018, 2017, all the way to 2016. Of course, it's physics. You need to spend a little bit, basically £10. You can ask your parents to assist you in acquiring these papers. You can get for November, you can also get for June down here, same. And you come and watch these videos as we solve them. And of course, if you are in need of coaching, I also do online tuitions. I am handling students online. On this site here, we call it SP Academy, spacademy.co.uk. The site I'm talking about is this one here. You can visit this site here, SP Academy. Of course, you can take time to explore the site. We offer ICT, mathematics, physics, biology, and chemistry. I need you to have a look at the student guide by clicking right here. Of course, you can also watch a video to get familiar with our online live classes. And once you make up your mind you need assistance, of course, you need to register if you have not already done that. And of course, fill this for us. Of course, you choose the student right there, and then you give the correct email address, because we need to you'll send you an email to activate your account. Once your account is activated, you need to sign in and then click here to find a tutor. My name is Godfrey. You can join me in my classes. I'll be glad to help you in spacademy.co.uk. I charge very minimally for one student. If it's one-on-one with you alone, I only charge you £35 per hour. If you bring in your 3 friends, so that you have 4 at any given time, I'll charge you a minimally of 25, not 20, 25 pounds per hour. So very fair price. Join me and let's get learning and help you get that your A star that you so desire. It will be easy. Very well. I wish you the best in you as you prepare for your exams. I hope these videos are of help to you. All right. This is question number 10B, and it was set on paper 4/2 of October, November 2019. Very well. Comparator, of course, it is 10B. That's why A is not here. A comparator circuit incorporating an ideal operational amplifier op-amp is shown in Fig 10.2. This is 10.2. This is a comparator. It compares the the voltage, the non-inverting and inverting voltage in there, and of course it does a function when the conditions are met. So we have here a variation with temperature theta of the resistance RT. RT is right here, which is the thermistor. The variation with temperature theta of the resistor RT of the thermistor is shown in Fig 10.3. This one here, of course. This is the resistance in kilo ohms, and this is the temperature on the x-axis in degrees Celsius. So as temperature increases, the resistance of the thermistor decreases. As usual, that is a negative temperature coefficient resistor thermistor. Part 1, right here, determine the temperature at which the light emitting diode in Fig 10.2 switches on or off. So the LED, we know that the LED will switch off or on when the switches on or off when the inverting voltage is equal to non-inverting voltage. Okay, and of course you can come up here. You can see the V plus is of course this 1.7 kilo ohm, that is the V minus right there. And of course our interest here is to find the temperature at which that happens. All right, so V minus is basically equal to you have to find that from the equation. V minus this one here. So this is a 3, and then of course we have this voltage here. So you use the potential divider formula. V is equals to V in times RT times R over R1, let's call this one R1, R1 plus R2. Use that equation to find V minus. So then this will be 3 times 1.76 kilo ohm. Of course, this is kilo ohm over 1.76 kilo ohm times RT, right? Right here. Okay, so this is R1 is 1.76 kilo ohm, this one here, and R2 is our RT. Okay, so this is 3 volts. That is what you're using down here. So we want to find the voltage at invertive voltage that is going in here. So what is the invertive voltage? Of course, when you do this, you can also find the non-invertive voltage, which is also going to be 3 times 1.2 over 1.2 plus 1.5. Of course, you're using the potential divider formula. So 1.5 is there, 1.2 is there. So the V plus here, non-inverting, will be 3 V in voltage times 1.2, yeah, because this is the one in here. So 1.2 kilo ohm, 1.2 kilo ohm over 1.2 plus 1.5 kilo ohm. Of course, the kilo ohms will cancel out. You don't need to bother with that. So then, what is our V plus? Our V plus. When you calculate our V plus, then you'll get some value, and remember, you can just equalize the two equations. We know that the inverter is equals to non-inverter. For this to happen, for this LED to switch on and off, therefore you can equalize the two equations. Yeah, let's say 3. You can equalize this equation and this. 3 times 1.76 over 1.76 plus RT is equals to this 3 plus 1.2 over 1.2 plus 1.5. I can just basically call this one 2.7. And of course, you can see that this and this will cancel. They appear on both sides. Yeah, and then what else will cancel? Okay, nothing else will cancel. So we can revert this one to 1.2 plus 1.5. So then you rearrange this equation and you'll find you get the RT over 1.76 is equals to 1.5 over 1.2, and our RT, we just write it here. Therefore our RT will be equal to 1.5 times 1.76 over 1.2, and this will give us 2.2 kilo ohm. So you look at the temperature, you look at the graph when the resistance is 2.2 kilo ohm. So temperature, you look at the graph to get temperature at this RT, which is 2.2 kilo ohm. Come to the graph here, and 2.2, this is 2, so these are 10, so this is 2.1, 2.2, 2.3, 2, yeah. So 2.2 is 1, 2, 2.2 is somewhere there. 2.2 kilo ohm, 2.2. So you draw a line up to draw a straight line to the graph there. Then you bring the graph down, bring the line down to get to the temperature. Very good. So this is 10, this is 15, so this is 14. So the temperature when RT is temperature at RT is equals to 14 degrees Celsius. It's equals to 14 degrees Celsius. So that is what you write right there, degrees Celsius. Very good. Part 2, state and explain. 2 questions there. Whether the thermistor is above or below the temperature calculated in here, which is 14, for the LED to emit light. We know that the LED, the LED, conducts when the LED conducts when V out is negative. So V minus should be equal to V plus, or then the inverting voltage should be greater than the invertive voltage, and an invertive voltage for that to happen, for the light to conduct. So our RT, the thermistor resistance must be lower, so that temperature is above 14 degrees Celsius. So we have stated state whether the thermistor is above or below. So the thermistor should be above 14 degrees Celsius. The explanation is that the LED conducts when the V out is negative, and therefore invertive voltage should be greater than this. So this must be RT must be the resistance of RT must be lower, so that the voltage is above, the temperature is above, so 14. All right. Of course, you can see if it is lower, then the temperature will be above 14. Very good. I hope that is of help to you. Look out for more topical questions from solvedpapers.co.uk site. Attempt as much as you can, and get ready for your exams. I wish you all the best as you prepare for your forthcoming 2021 and beyond June and October exams. Hope to see you in my next video. Cheers.